Built with power and price in mind, the Perkins 8-liter was supposed to be the perfect fit for mid-size cranes. But it didn't take long before operators began to complain. From cracked blocks to oil starvation under heavy loads, this engine's story became one of risk, regret, and for some, redemption. When Perkins introduced their 8-liter engine, it was hailed as the solution that construction and heavy equipment industries were waiting for, particularly in crane applications. It aimed to deliver a combination of power and compact design that could address the growing demand for higher performance in smaller, more fuel-efficient packages. The timing couldn't have been better. Environmental regulations on emissions were tightening, and manufacturers needed engines that could balance raw capability with compliance. The 8-liter engine was positioned as an industry-defining innovation, and early signs suggested it was poised to meet those expectations. At the heart of the excitement was its ability to deliver impressive torque in a relatively compact design. For cranes, this was a critical factor. Operators require not just sheer power, but also the ability to sustain that power consistently under load. This engine promised to do exactly that while taking up less physical space, which opened up new possibilities for crane design. Smaller engines could mean lighter cranes, better fuel efficiency, and, in theory, lower operating costs. Perkins also marketed this engine as a step forward in clean technology, promoting its compliance with Tier 4 emission standards. These standards were challenging for many manufacturers to meet, especially without sacrificing performance. So the 8-liter's ability to combine clean operations with strong output generated enthusiasm across the industry. Of course, Perkins wasn't starting from scratch in the heavy equipment engine market. They had a trusted reputation to build upon. Their 6-liter phaser engine had been widely adopted and earned recognition for its consistent performance and reliability. Later, the 9-liter 1700 series further cemented Perkins' standing as a leader in the industry, balancing larger power output with durability that satisfied even the most demanding applications. The pressure was on for the 8-liter to live up to these standards and even surpass them. Industry insiders anticipated that this new model would represent a perfect middle ground, bigger than the phaser, but more compact and efficient than the 1700 series. The stakes were high. Perkins wasn't introducing just another product. They were launching what they hoped would be a cornerstone of their future lineup. Adding to the hype, one of the first major adopters of the Perkins 8-liter engine was a well-known crane manufacturer looking to set itself apart in the competitive market. Early deployment was framed as a success story, with cranes reportedly benefiting from the engine's torque delivery and compact size. Engineers praised its adaptability, and the initial reviews indicated that it could handle the demanding lifting tasks required on job sites. This sparked conversations across the industry, with many speculating that Perkins had redefined what was possible in crane engine design. The combination of power, reduced emissions, and compactness gave the impression that the 8-liter engine was a technological leap, not just for cranes, but for heavy equipment in general. However, some challenges began surfacing even in the earliest phases of rollout. Although these issues were subtle at first, they hinted at potential flaws that could become major problems as the engines were exposed to real-world usage. For one, reports from testing situations suggested that maintaining consistent power delivery wasn't always guaranteed under extreme conditions. While most day-to-day operations performed as expected, operators occasionally noted uneven response during tasks involving variable loads, such as dynamic lifts or extended usage at high capacity. These isolated incidents didn't seem significant at the time, but they introduced questions about the engine's long-term dependability. Another early indicator of trouble was the engine's performance under prolonged strain. Heat management became a talking point among engineers, with some suggesting that cooling the engine effectively required more than anticipated. It wasn't an outright deal-breaker in the beginning, but the fact that cooling hardware often had to be scaled up offset some of the space-saving benefits of the compact engine. These were relatively minor concerns at first, though, and many manufacturers chose to overlook them, focusing instead on the opportunities the 8-liter engine promised. The sense of optimism around its potential outweighed the uncertainty of these early warning signs. Looking back, it's easy to see how the incredible buzz and expectations surrounding the 8-liter engine created an almost unfairly high bar for it to clear. By building on the success of earlier models, Perkins didn't just aim for incremental innovation, they set out to redefine industry standards altogether. The result was an engine that captured attention and sparked excitement, but may have been overburdened by its ambitious scope. In striving to balance compactness, efficiency, and power, it became clear that the smallest imperfections in design or execution could ripple into larger problems once the engines left controlled testing environments. Ultimately, what the Perkins 8-liter engine represented at its launch was a promise that cranes could perform better, operate more cleanly, and save on weight and fuel without sacrificing reliability. How far could this engine take the industry? It was positioned to be a cornerstone for the future, the answer to evolving needs in both emissions and efficiency. But the very ambition that made the 8-liter so bold also made it vulnerable. High hopes left no room for error, and when subtle issues started to show, the question wasn't just whether the engine would perform, it was whether Perkins had overstretched its grasp. But how did this promising engine go from a game changer to a cautionary tale? Let's examine the cracks that started to show. Could the ambition to pair power with efficiency have been the Perkins 8-liter engine's undoing? For a component so central to a crane's functionality, the expectation was clear: deliver torque smoothly and reliably under immense stress. Unfortunately, this engine often fell short, posing problems that were more than just technical inconveniences. They directly impacted safety and operations on job sites. Operators quickly discovered the engine's power delivery inconsistency during tasks that required precise control. Instead of the steady torque that cranes rely on for stability during lifts, there were fluctuations that made operations less predictable. These inconsistencies, while minor at first, led to jerky or imprecise movements during variable loads, creating situations where exact performance was not just desirable, but essential to prevent accidents. One crane model that faced these issues firsthand became a symbol of frustration among industry professionals. Reports surfaced detailing the catastrophic failures caused in part by the engine's flaws. During high-stress lifts or when duty cycles demanded extended use at heavy loads, the Perkins 8-liter engine's weaknesses were most exposed. For example, on construction sites where these cranes were used to lift uneven loads like heavy beams or large components, the torque delivery proved unreliable in ways operators could not easily compensate for. Imagine hoisting a steel beam above a work zone only to have the engine momentarily fail to maintain torque stability. The result wasn't just an inconvenience, it presented real danger to workers and equipment alike. In several instances, these failures caused projects to grind to a halt, with repairs delaying timelines and tarnishing the reputation of both the engine and the machines running it. Overheating presented another significant and recurring challenge. Engineers had worked to balance heat management with the engine's compact design, but job site realities quickly revealed this balance was fragile. Under heavy operation, the 8-liter engine struggled to manage heat effectively, especially during prolonged tasks. This forced crane manufacturers to incorporate larger cooling systems to keep the engines running within a safe temperature range. Originally, one of the primary selling points of the 8-liter engine had been its compact design, meant to reduce the overall size and weight of the cranes in which it was installed. But with oversized cooling systems now needed, these advantages were eroded. The larger radiators and additional cooling components took up space, added weight, and forced design changes manufacturers had not initially planned for. For equipment owners and operators, these heat management issues didn't just affect crane design. It also brought on an avalanche of practical problems. As cranes endured downtime for overheating repairs, projects were delayed and costs mounted. Operators reported being forced to monitor engines more frequently to prevent shutdowns mid-operation, further reducing efficiency. Feedback from manufacturers and users alike often cited extended downtime and higher maintenance costs as barriers to relying on the Perkins 8-liter engine. In smaller fleets where operators depended heavily on timely job completion to retain clients, these delays could be devastating. When compared to competitors like MTU engines, the deficiencies of the Perkins 8-liter became even more stark. MTU engines, such as the Series 6R1500 or the 6R1000, were built with consistent performance under industrial use as a priority. Cranes equipped with MTU engines, like the Terex Demag AC300-6 or AC45 City models, highlighted this gap with fewer complaints of torque variability or cooling limitations. Even within Perkins' own lineup, the older 6-liter phaser engine maintained a reputation for reliability. Customers began looking at these alternatives, recognizing their practicality over the frustrating track record of the 8-liter. The long-term effects of these flaws on job site operations weren't just financial. They also deeply impacted customer confidence. Cranes equipped with the Perkins 8-liter engine tended to become associated with unexpected complications. Repair costs for overheating components added up, causing some owners to question the value of their investment altogether. For equipment manufacturers relying on Perkins engines, these issues pose reputational risks of their own, as dissatisfied customers pointed fingers not just at the cranes, but at the components powering them. Over time, the damage spread to Perkins' credibility, particularly in the construction and crane industries, where reputation is hard-earned and easily lost. Perhaps the most telling insight came from the operators themselves. Many described feeling increasingly concerned about safety whenever the crane's engine hesitated or struggled under heavy workloads. On job sites that required precise, high-stake operations, such as setting girders or hoisting materials in tight parameters, confidence in the machinery was crucial. Once an engine developed a reputation for unreliability, its impact went beyond individual units. It shaped purchasing decisions across the industry. Companies began to choose other suppliers who could offer a proven track record of consistent operations. Putting everything together, these flaws represented more than an engineering oversight. They revealed a fundamental gap between the features the Perkins 8-liter engine was marketed to provide and its real-world performance under demanding conditions. The combination of torque inconsistency, heat rejection issues, and increased operating costs not only delayed projects, but also became a cautionary tale for even the most loyal Perkins customers. At its core, the engine's problems weren't isolated to a handful of cranes. They reverberated across construction sites, supply chains, and industry perceptions. This left Perkins scrambling to address the fallout as industry professionals grew skeptical of their latest innovation. So what lessons can we learn from these failures, and how did Perkins try to address them? The failure of the Perkins 8-liter engine left an undeniable mark, forcing the company to face some difficult truths about its design and testing processes. The backlash from customers was immediate. Manufacturers and operators who had placed their trust in the engine's promise of efficiency and power were instead faced with repeated downtime, costly repairs, and operational headaches. In an industry where reliability defines reputation, these problems had serious consequences. As word spread about the engine's flaws, unpredictable torque delivery, heat management issues, and overall poor performance under stress, confidence in Perkins took a significant hit. Perkins couldn't afford to treat this as just another misstep. Instead, these failures became a turning point. Perkins quickly realized that regaining credibility wouldn't come from small tweaks or marketing fixes. The challenges exposed by the 8-liter had highlighted key gaps in their engine development and testing processes, particularly for applications as demanding as cranes. In response, Perkins began an internal shift, implementing deeper evaluations during development to better simulate real-world conditions. It was a necessary change, considering the stakes weren't just about producing engines, but about reclaiming their position as a trusted name in construction and heavy equipment. This shift led to the creation of the 9-liter 1700 series, which directly addressed the fundamental flaws that had plagued the 8-liter. The Perkins 9-liter 1700 series emerged as a solution designed with lessons learned from the 8-liter's failures. For starters, it tackled the heat management issue head-on, focusing on a low heat rejection design. This resulted in fewer cooling requirements, which meant manufacturers no longer had to install oversized radiators just to keep the engine running, a significant improvement. This wasn't purely about convenience either. By reducing the size of required cooling systems, the 1700 series also allowed for simpler, more compact crane designs, restoring the advantages the 8-liter had originally promised. Additionally, the new engine introduced efficiencies in torque delivery, creating smoother power curves that supported stable, predictable operations even under the strain of heavy loads. Beyond technical improvements, Perkins made practical changes to demonstrate their commitment to reliability and reduced downtime. The 1700 series featured service-free after-treatment systems and extended oil change intervals of up to 500 hours. For operators and manufacturers alike, this translated into reduced maintenance costs and less need for frequent servicing, a marked contrast to the maintenance challenges associated with the 8-liter. Additionally, by including on-engine after-treatment systems, the 1700 series offered a streamlined design that reduced installation costs and complexity. These advancements highlighted a newfound focus on real-world usability and cost-effectiveness, essential for rebuilding trust in the market. The 9-liter 1700 series wasn't just a recovery effort, it was also a demonstration of Perkins' ability to innovate under pressure. The engine met strict emissions regulations, including EU Stage 5 and US EPA Tier 4 Final, while maintaining strong performance. Its 6-cylinder, turbocharged and aftercooled setup delivered a power range of 250 to 340 kilowatts, 335 to 456 horsepower, providing the strength needed for demanding crane applications without sacrificing efficiency. This combination of power and compliance aligned perfectly with industry requirements, giving Perkins a legitimate chance to regain a foothold in the market. In comparison to its competitors, the 1700 series finally represented a product that could compete on both reliability and performance. At the same time, Perkins recognized that customer expectations were evolving. The problems with the 8-liter had illuminated the risks of relying solely on diesel engine solutions in an industry moving toward sustainability and innovation. To keep pace, Perkins began to diversify its product offerings, introducing hybrid power technologies targeted at construction applications. At Bauma 2019, the company revealed hybrid electric, hybrid mechanical, and hybrid hydraulic systems, marking a significant step in addressing the growing demand for efficiency and reduced environmental impact. Unlike traditional diesel engines, these hybrid solutions offered flexibility and adaptability, allowing manufacturers to optimize their equipment for specific uses. Each hybrid system brought distinct advantages to the table. The hybrid electric technology, for instance, was designed to deliver significant fuel savings while minimizing installation complexity. Meanwhile, the hybrid mechanical solution incorporated a high-speed flywheel to store and release energy during cyclic operations, ideal for machinery requiring intense bursts of power. The hybrid hydraulic option, on the other hand, stored energy in hydraulic accumulators, which could integrate seamlessly into existing equipment. These approaches demonstrated Perkins' determination not just to recover from the 8-liter setback, but to redefine its approach to meeting the needs of tomorrow's heavy equipment. Internally, the story of the 8-liter engine became more than just an embarrassing chapter. It became a profound lesson in how not to approach development. Perkins engineers began treating the 8-liter's failures as a cautionary tale, a reminder of what can happen when ambition overshadows thorough preparation. It sparked deeper conversations within the company about ensuring durability, predictability, and performance under the harshest conditions. These discussions directly influenced not only the 1700 series but also Perkins' broader strategy, leading to innovations that kept the company relevant in an era of rapid technological change. Ultimately, the setback of the 8-liter engine forced Perkins to reevaluate nearly every facet of its approach, from design to customer relationships. By using that failure as fuel for transformation, they not only avoided further reputational damage, but also positioned themselves as a company ready to lead through innovation rather than rest on past success. The launch of the 9-liter 1700 series and the move toward hybrid technologies weren't just product decisions. They were symbolic of a company learning from its mistakes and adapting to the challenges ahead. But what does this story mean for the future of heavy equipment engines and the lessons we can all take away? The Perkins 8-liter engine began as a bold idea but quickly became a cautionary tale, showing how ambition without proper execution can lead to significant setbacks. Its failure serves as a reminder that even respected names in engineering can stumble when gaps in testing and design emerge. However, the legacy of the 8-liter is not just about what went wrong, it's about how Perkins responded. By addressing flaws and prioritizing adaptability, They reinforce the importance of learning from mistakes. If you've faced challenges with heavy equipment, share your experience in the comments. And don't forget to subscribe for more industry insights.